Okay, the maximum posteriori. So in this case, I'm just doing the same dance as I did with maximum likelihood, but in this case, I'm taking the prior here, right? So same dance, take the derivative. It really doesn't. It's not super crucial, but the biggest thing I want you to know actually is that these conjugate priors exist, and they represent encoding your prior information. And usually, anything you work with, they're pseudocounts. As the data grows, your prior the influence of the prior will shrink, minus the kind of pathological cases. So even though I wouldn't ask this question, you could ask something like true or false. As the data goes to infinity, the prior has no effect. It's true for real life, but it's actually technically false because you could weigh your prior so heavy that it drowns out your data. I guess when it goes to infinity, but if I said, I give you 1,000,000 examples, does your prior still have an effect? And well, if I put enough pseudocounts, yeah, sure. Right? I could put 10 to the 12 heads as my prior. It's kind of this pathological question. It's a popular question.
As the prior goes to infinity.
What?
The prior is going toward
yeah, exactly. Right. So, but anyway, I don't know if everyone follows what I said. It's not. But in general, as the data increases, your prior has less effect. For the obvious reason, I added one head and one tail, and as I observed 1,000 coin flips, it no longer matters.
So, for instance, just really quickly on the homework, we saw all those many documents.
Yeah.
And they all had some kind of word count, but
yeah.
we had many examples, so the data was pretty good, right? So we would not really work with a conjugate prior for.
So you did use one. You used a Dirichlet, right? This has to do more with Bayesian kind of having some computational problems, but actually, if you think about it, you added a 1 for every word,
right?
Effectively. So and you had I don't know how many documents, 1,000. I don't remember now, but thousands of documents.
2008 in training.
2,100 voices string.
Thank you. So, thousands. If I was to give you 1,000,000, you would expect the estimates to reflect the true distribution more than if I was to only give you 50 documents and you added a 1 to everything. It actually might have an effect. Right?
You also modified the data,
I
right?
cheated anyway. I gave these a tested vocabulary.
Top and upgrades were just new.
That's true. I also did this, that I got rid of words
and
got rid of words that didn't occur more than 3 times. But, yeah. Yeah. Okay, multinomials. I'm mentioning them. You've used them. The math is the same, just with multiple outcomes instead of just 2. Continuous variables. We talked a fair amount about Gaussians. The prior. So the conjugate prior of a Gaussian. I didn't ask, but it's a Gaussian. So, because if you think about it, you're specifying a mean and a variance. In the case of a Gaussian, all you can do is specify a mean and a variance, like what you think the mean and variance is, and the math works out well.
You would just blow up the mean and variance a little bit?
Well, you essentially what you do is you say, so I have a mean and a variance, and when you, so what you will do is the variance will be a product, and then the mean you shift. I don't want to spend all the time talking about God, but yeah, I mean the basic idea is if I was to specify what I think the mean is, then the new mean becomes a weighted average of my prior mean and the mean I observed from the data, effectively. And my variance, if I think it's a big variance, but it's actually, I observe a thin variance, effectively is the spread, right? So it's a product. And that's kind of reflected here with the math. I mean, this is not the math for that problem, but just that it has some nice properties. And it's something you do all the time. Actually, the thing about a lot of priors, when I describe them to people, it's things they do anyway, they're just not formalizing it. So if I was to tell you that, I can't think of a good, but if I was to say, oh, we observed a population of people, and their height, the average height was 5'2", and the variance was, you know, whatever. What people would do would be like, unless there's something special about this population, like clearly the mean's off, and shift it over. And clearly it's not that peaky. Spread it out, and this is just a way of controlling it. Multivariate, not interesting. Again, so maximum likelihood, same thing. So these are our parameters. This is our data. So it's a product of several examples. So this is our likelihood function. This is our log likelihood function. And then we just take the derivative of the log likelihood and minimize, which I assume I did. So yeah, so here's my log likelihood. If I take the derivative with respect to mu, I'll get what everyone does for the biased estimate of Gaussian. And if I take the derivative with respect to the variance, I get the function for the variance. Okay. I already spoiled this for everybody. So the conjugate prior is a Gaussian, and if you see here, then I'm throwing away some stuff, but this is my prior, this is my data, and if you do the math, it just kind of works out. And it's what you'd expect, like I said, is that the mu effectively is you're moving the mu over.
That's mu naught, or that's sigma naught, right?
Sigma naught.
Sigma 0 to the second.
Here?
Mm.
No, I think it's still in there. It's just that it's if you specify both, because what you're going to do is, actually, am I wrong? I'm too lazy to figure it out now. Yeah. Anyway, I probably actually. I'm going to skip it. So these are some other that you don't need to know, but that I just wanted you to know there's pairs. That's all. That Dirichlet's multinomial, gammas for unknown variance Gaussian. Okay. Density estimation. So again, this is just a case of estimate the parameters that with the data. Why am I saying this? I don't know why. Okay, let me just see. So this is we already covered this. Oh, okay. So generative models. Maybe this sentence will mean more as I say it now. So what we're doing is we're modeling how the data gets generated. So the way you should think about it is there's some machine that's generating outcomes in the universe. We're going to be deists for the moment. And what you're really doing is you're just specifying the probability distribution that you think is generating the data. So for naive Bayes, our story was two classes, flip a coin, based on that coin, multivariate, you get a box of coins, you flip all those coins, the die, or the multinomial is what you did in the homework, you receive a die and roll the die over and over. In the EM homework, the story is that your authors are essentially just length producing machines, which by the way, that model, even though the example I give is stupid, it's actually used in medicine for survival curves. If you have an unknown disease, but you observe a sequence of survivals, that you can estimate it, like what's the clustering of diseases and things like this.
Do you remember the zombie apocalypse?
Yeah, right. There's a mystery disease. Yeah, but in any case, the generative story there is flip a coin, and authors in this case, they don't even write books. All they do is spit out, this is how long my chapter would have been. That's really all authors are. Generative stories are usually ridiculous, but they work. So that's a good thing. You're better off with ridiculous things that work as opposed to sensible things that don't. So, anyway, so you model predictions based on the probability of the model generating the given data. So you're doing this is a way to model a joint probability distribution. And, yeah, okay. Hidden marker models, you don't care. Language models, you don't care. There. All right, so in this case, this is a stupid generative story of I have 2 coins, pick your coin and then flip it. And I don't wanna kill the whole time.
You do this on the practice.
I do this on the practice again, yeah. So it's a good question. Even though on the practice is I think a little trickier, but anyway, but it's very close. We'll see. Yeah. So yeah, I don't know what to say particularly. I guess any questions about? I mean, Bayesian learning. I'm gonna, as I receive more data, update my case. What?
The slide's PhD.
Oh, that's cute. That's good. Wasn't intentional. Yeah, I mean, I worked through an example here, but I guess are there any specific questions? Like, if people understand parameter estimation enough to not have me keep on doing this over and over. I'm lost now what I originally said. So Bayes optimal classifier. I mentioned map and MLE. If you wanted to combine multiple classifiers, this is one way to do it, where I wouldn't actually take the maximum or the maximum history or estimate, but I would blend the different classifiers. I never gave you a problem on this, so you're not responsible. When we get to ensembles, I'll probably review this again. No. And this was just me motivating. We're going to get to naive-Bayes. Okay. Stop me if you have a question. These are mostly previous slides. This is all generative model. The justification is just that our model does actually generate the data. That's really the assumption. So as I get infinite data, I will estimate the parameters correctly. So if my joint probability distribution does have conditional independence, given enough data, naive-Bayes will learn the best classifier. If it's not, then I'll get more error than the best. I'll get a suboptimal classifier if my assumptions are wrong. But even then, I will, unless my assumptions are horribly wrong, as I get more data, I'll probably push down the error, but you could pick a better algorithm.
Naive-Bayes starts on page 33.
Yeah, so the point here was just, thank you. The point of this was just that you can't estimate the joint, you just never get enough data. I gave that as in the class after this, I gave a homework to, I went through an example of that more clearly, I think. Where did you say?
Page 30.
Okay, naive-Bayes. So, naive-Bayes, everyone knows it by now, but this is just my chain rule, kind of plug through. Over and over. So you have